So good day to everyone. I'm very happy to present our next seminar speaker, Lior Suchoy. Lior, מי שמכיר, those who knows, he did his bachelor degrees in geology and physics in the Hebrew University of Jerusalem. Then he did his master degree in the University of Haifa in collaboration with ETH in Zurich. He moved to a PhD in the in Imperial College in London, which is one of the best universities in London. He's doing his PhD under the supervision of Saskia Ross, and he's very interested in tectonics and especially in the Mediterranean and the Levant. He did his master on the Cyprus Arc. These days he's doing numerical modeling, 2D and 3D, and numerical modeling of subduction and non-linear subduction models. And today I believe we'll hear a bit about his PhD, and we look forward to hear. At the end of the talk, you'll have the option to just go on and ask questions, and let's share the screen from you to you, Lior.
Okay, thank you for inviting me. This talk will be held in English because I invited a couple of collaborators. I don't know if they've joined already or not, but I don't speak Hebrew. But please feel free to ask questions later, both in English and Hebrew. A second, please, I'll share my screen. Okay. Can everyone see it?
Yes.
Good. Okay, so with no further ado. Again, thank you for inviting me to talk today. This is my work on the effects of asthenospheric drag on subduction dynamics. It's a work I've been doing with my collaborators, Saskia Ross, Benjamin Maunder, Fanny Garel, and Rodri Davis. Oh, okay, perfect. So just to give us some context, this is the normal sort of textbook sketch that we think of when we think about the tectonic system. And the engine behind this system is the subduction. So more specifically, this section of the system. Examining the subduction system, we mostly focus on the subducting plate. Now, this plate begins at the mid-ocean ridge. It moves towards the trench, where it bends and moves into the mantle. The forces involved in this process include much different forces, but the main one, the one that drives subduction, which again drives tectonics, is the slab pull. Now, slab pull is the difference in buoyancy between the slab, the subducted part of the subducting plate, and its surrounding mantle. As I said, it is the main force, but there are other forces as well. So we can think of ridge push, for example, but it is minor in the sense that it is about 10% of the magnitude of slab pull, and it's a contribution to subduction. On the other side are resistive forces for subduction. So I will focus today on the bending of the plate and the basal drag. Of course, there are other forces which I will not go into. Bending of the plate, meaning the ability to deform the plate, requires a lot of energy. Most of this energy is spent around the bulge near the trench. So this is where most of the deformation of the subducting plate happens. Another plate, and this is the main focus of this talk, is basal drag. This is the drag that is being exerted by the upper mantle on the bottom of the unsubducted part of the plate. So this is not the drag around the slab. This is only the drag that is at the base of the unsubducted part. Okay. My main question in this study and others is whether this force, the basal drag, is important for subduction dynamics. this question had been asked by other groups, and the main evidence being used to answer it is the ratio between subduction velocity and the size of plates on the Earth. Now, the logic behind it is quite simple. The bigger the plate, the more drag, more basal drag it has. Therefore, if basal drag is an important force, we expect basal drag to reduce velocity. So in a way, we expect velocity to drop with the size of the plate. However, when people actually plot velocity versus size on the Earth today, and this is only for subducting plates, of course, we don't really find any correlation. So I put a fit line here, but you can see the fit is very, very poor. We can't really say in any way that this is a way to explain behavior on the Earth. So size is not a good predictor of velocity. Others have looked at these findings, more specifically Conrad and Hager in 1999, and of course groups before them, and concluded that drag, therefore, is a minor force in resisting subduction. Okay, another set of evidence that is being used to discuss this topic is the global trench motion on the Earth. So what you see here is a work that had been done by Hoss, 2011, about the trench motions throughout the Cenozoic. Now, through this period, what we see is that most trenches, about 80%, retreat. There are about 20% of the segments of trenches, again, throughout the Cenozoic, that tend to advance. But both the advance and the retreating trenches seems to move in very minor ways. So we don't see large motions on the Earth in the reconstruction. On the other hand, when people have modeled subduction, most of the models tend to see a retreating trench that is very significant. The amount of retreat is quite high. The only models that were able to reduce the amount of retreat and also to get both signs, also retreat and in some cases advance, are models that reduce the strength of the asthenosphere. So the asthenosphere is the upper part of the upper mantle, and reducing its strength directly reduces the value of drag in those models. So if by reducing the asthenosphere's strength in these models, we get more Earth-like results, that gives us an indication that maybe on Earth, really, the asthenosphere is quite weak and basal drag is not a significant force. So again, maybe the answer to our question is no. Then on the other hand, there are global models of mantle flow. And this is an example from Conrad and Lior Bertelloni for 2006, that they have looked at how the mantle behaves globally and extracted from these models the forces that the upper mantle exerts on the plates. So again, this is a direct measure of drag. And they found, if we sum up the traction values for all of the subducting plate, we find quite high values at each plate. So they actually gives us an indication that the value of forces, the absolute value, is quite high, and maybe it is a significant force. So to settle this contradicting evidence, we did a very simple back of the envelope calculation where we directly calculate the drag and the pull forces of different plates. Now, we can do that because most of our evidence are there. We know global velocities, we know plate geometry, we know things like lithospheric densities and so on. And we can estimate the volume of slabs and the viscosities of both the plate and the mantle. We use relatively simple functions to calculate both the basal drag and slab pull. And what we find is that for a fairly big plate, like the Pacific plate, we get a ratio between the drag force and the pull force that is about 16%. Now, just to remind you, when I mentioned trench push, sorry, not trench, when I mentioned ridge push, I said it was about 10%. So this is about 150% of the magnitude of ridge push. Now, on the other hand, when we look at a relatively small plate, like the Caucasus, we find that this ratio drops to about 5%. So that means it's about half of ridge push. We use ridge push as a sort of threshold for significance. So we say that in this case, the basal drag on the Pacific seems to be quite significant, while the basal drag on the Caucasus seems to be less significant. So these evidence have been examined by other groups as well, and they suggested all kinds of solutions to the reason why the apparent drag seems to be high, and yet we don't really find any correlation between velocity and plate size on the Earth. One group suggested that the strength of the lithosphere, the viscosity of the lithosphere that we're using in our calculations, and that includes very simple calculations like what I've just shown, and also models, the lithosphere there is not strong enough. By increasing the strength of the lithosphere, what we are able to do is make the deformation of the plate much more expensive. And this way, bending becomes actually the main resistive force in subduction and not basal drag. So it's not that we don't calculate basal drag correctly, it's just that by calculating it, we're not taking into account the main resistive force. This is the hypothesis anyway. Other groups have looked at the value of drag directly through the viscosity of the asthenosphere. And they claim that actually we're using values that are too high for the asthenosphere, viscosity values that are too high for the asthenosphere. And by reducing these values, we are able to reduce drag and actually get a more Earth-like result. There's a third hypothesis that didn't focus on one or the other, but on the ratio. So ratio of the viscosity of the lithosphere to the viscosity of the asthenosphere. And they claim that the higher the ratio, the less significant the drag is. So following this evidence and these hypotheses, we set out our models to examine the problem. We used a system called Fluidity to design a 2D thermomechanical model. It applies the Stokes and Buzinski approximation with the assumption of mass, momentum, and energy conservation to solve for motions. The highlight of our model is that we use an Earth-like nonlinear composite rheologies, which are temperature, strain rate, and pressure dependent. That means that we're able to incorporate together different creep mechanisms, and we are able to put a complex, again, nonlinear function to solve for them. We're able to do that because we have an adaptive mesh integrated into the model. So an adaptive mesh is a mesh that changes its cell size and node location through the run of the model. What you can see here is our initial condition, and those blue dots and lines is the mesh as it's plotted at part of the model. So the adaptive mesh actually allows us to take into account changes in the model. Where the model changes significantly, we can reduce the size of the mesh, and where things are relatively constant, we can increase the size of the mesh, therefore saving a lot of a lot of computational power. So for example, in our initial condition, we assume that there isn't much motion and much change happening in the lower mantle. So that's why you can see that the mesh there is relatively coarse. And then when we focus on the trench, which is the rectangle at the top center of the background image, and then if we focus even further into the decoupling between the subducting plate and the overriding plate, we can see that our decoupling layer is actually solved very, very well in very, very fine details. Now these change from very fine, about half a kilometer squared grid size, to the case of the lower mantle, where things can be over 100 kilometers square grid size. Again, this is the initial condition for our model. So we, in order to account for basal drag, compare long models with short models, but apply exactly the exact same rheology for both, and use the same initial slab for both. So our pool should be the same. And apart from basal drag, pretty much everything else should be the same. Our long models are 10,000 kilometers long, the box, which is divided in the middle into 5,000 kilometers subducting plate. So that's from the left side up to the center. And then a 5,000 kilometers overriding plate from the right side to the center. There are ridges at both sides. You can see the ridge on the subducting side, and the ridge on the overriding side is masked by the mesh nodes. Our rheology is an emergent rheology. It's not something prescribed. It's not a material field that is prescribed, but it is the result of our initial temperature field. And later it is the result of the temperature, strain rate, and pressure field. So this actually allows us to account for a lot of changes that are hard to account in other models. Things like free trench. Our trench is not fixed at one place. Our ridge as well is not actually fixed. And the thickness of the plate changes with time as the plate cools, or when it moves faster, it heats. Yes. So the bottom of our plate is determined by the temperature field and not necessarily by a fixed material field. Okay, about the boundary conditions. So because everything is thermally, is used by a thermal field, we apply a top and bottom thermal boundaries. The top is 0C, the bottom is 1300 C. The bottom of the model, of course, is the bottom of the lower mantle. We don't allow for any heat flux from the sides. We apply a free surface at the top. So this is this is an actual free surface, not a sticky air or something else that is being used in other models. And free slip on any other boundary there. Yes. Well, for some of our results, and I hope you can see the animation well. This is our reference model. And as I mentioned, we are comparing the long and the short models. So before I'll go into the results in depth, you can already see that the behavior between the long and the short model is different in many ways. So there's definitely much more trench retreat in the long model, and it appears to have more of the material flowing into the lower mantle at the short model. Now, you can see that as well if you look at the plot of the data that I added at the right side. This is the displacement, and it's both for the plate and for the trench retreat. Now, you can see the short plate as the dashed line and the long plate as the solid line. The trench is marked in yellow and the subducting plate is marked in red. And what I said about the animation can be shown in the graph. So there's, again, much more trench retreat for the solid line than for the dashed line. and apparently much more plate flowing into the mantle for the dashed line over the solid line. Yes, if we look at the amount of material that flows into the mantle for the long plate, we actually find that it's quite similar to the amount of trench retreat. So we expect both mechanisms to contribute the same for subduction. That is, of course, not the case for the short plate. Okay, looking more in depth with the results. So the central top graph is the one I just showed you on the previous slide. We can look at the velocity for these models. And what we find is, as expected, that the trench of the long plate actually moves faster than the trench of the short plate. We also see that the plate itself for the short plate moves faster than the long plate. So that's, again, things that were directly observed from the model. And if we take the ratio of trench retreat to the overall material converged, so the overall material converged is the sum of trench retreat and amount of material flowing into the mantle, we can see this trend that I just mentioned, that trench retreat plays about 50% of the mechanisms active in subduction for the long plate, while it plays about 20% for the short plate. But this talk focuses on forces, so we can directly calculate the forces. And as you can see at the bottom left graph, the pull force in our model is much higher than the drag force. That's of course good. We kind of expecting that. So I plotted both of them just to give you a sense of the ratio. Then I zoomed in on the basal drag force. But what we actually care about is not the absolute value of one or the other, but the ratio of the two. So that is the bottom left graph. In this graph, you can see that there is a constant behavior for the basal drag significance. And significance, again, is the ratio of basal drag to slab pull. So this significance rises at the beginning of the model, then it drops as the model progresses. And yet, we can see already a trend in this graph, and that's that the significance of basal drag in the long model, so that's the solid line, is always higher than the significance in the short model. Now, to take you back to our back of the envelope calculation, that fits with what we see on the Earth. Basal drag is, on the Earth at least, appears to be more significant for bigger plates. So that's, anyway, a good indication that we're on the right track. Now, as I mentioned before, there are hypotheses to reduce the significance of drag, and we set out to test those hypotheses. So in order to do that, we had to define different parts of our model. Now, as I said, we don't have a material field, so we had to use other parameters. We defined the plate to be the area of the model that is colder than 1100 C. And then we divided it into the subducting lithosphere and the overriding lithosphere. The subducting lithosphere includes, of course, the slab and everything that is left of the trench. The overriding lithosphere is everything right of the trench. We also defined the asthenosphere as everything that is between the 1100 C isotherm and 220 kilometers depth. Of course, that's excluding the slab. So the models that we set out are one with a weakened asthenosphere. Again, that's one of the mechanisms mentioned before. We put a factor of 0.5 on the viscosities of everything that falls within the asthenosphere. Now, this is a nonlinear model. So that means that by reducing the value of viscosity in the asthenosphere, we create a feedback effect. So by reducing the viscosity, we actually allow for velocities to be higher. The higher velocities, of course, generate higher strain rates, and these in turn weaken the asthenosphere even more. So even though we set out to weaken our asthenosphere at about 50%, we ended up with an effective weakening of about 90%. And that's why when we compared that to a stronger lithosphere model, we used a factor 2 and a factor 10 for the strength of the lithosphere. Okay, so these are our three models, a 0.5 factor for the asthenosphere and a factor 10, factor 2 for the subducting lithosphere. So just to give you a sense of how these models develop with time, this is the final stages of all of our model. So the top left side is our reference model. And then at the top right side, we have the model with the weak asthenosphere. The bottom left is the strong lithosphere with the factor 2, and the bottom right, a strong lithosphere with factor 10. Now, again, without going into the results yet, we can already see that these develop quite differently. So we can see, for example, that the long reference and the long weak asthenosphere, so the top two models, they have much more buckling. You see much more of those curvatures along the trench, along the slab, than you see with the strong lithosphere. And to be more specific, with the very strong lithosphere, the factor 10. You see different shapes of the edge of the slab. And of course, you see different amounts of trench retreat. So just to give you a sense of how different those models behave. Now looking more in depth into the results, and this is only the plate behavior. We'll get to the trench behavior in a minute. What you see here is in color, the results from the models, and the background pinkish color is our reference model. So everything is compared to the reference. By applying a weak asthenosphere, we see that the plate moves much more into the mantle. But the additional movement of the plate is similar for the long and the short plate both. That means that drag still plays a significant role, because if drag wasn't significant, we would expect both of these curves to merge together. What we see is the gap between those two curves is still significant. You can see that as well if you look at the relative force, so the bottom left graph, where the significance of drag in the long model is quite higher than the significance of drag in the short model, and is definitely not null. It is, however, somewhat reduced from the reference case, but not enough to make it insignificant. Looking at the strong lithosphere model, we actually have a more complex behavior. So the long models with the stronger lithosphere appear to behave very similar to the long reference model. So we see that the solid lines pretty much stay the same place. The main difference is the behavior of the short plate. Now, we interpret this as a dependence of the long plate on drag. So by increasing the strength of the lithosphere, we make it harder to bend. But since drag plays a significant role for the long plate, we actually see not much of a change to its behavior. For the short plate, where drag plays a less significant role, we see quite a significant change to behavior. So it's much harder for new material to bend before it enters the lithosphere, before it enters the mantle, and therefore we see much reduced amount of material flowing into the upper mantle. In all cases, drag is still significant with regards to pull, But as I mentioned before, the case of the short plate is that there is another force that is now acting as the most important resistive force. Looking at the trench behavior, we see that for the weak asthenosphere, weakening the asthenosphere actually allows us to reduce trench motion. So that is, again, a good indicator because, as I mentioned in the beginning, trench behavior on Earth is less prominent than the one we see in our models. So by reducing the amount of trench motion, we're actually getting a more Earth-like behavior. However, we still see the difference between the long and the short plate. So drag still accounts for a different kind of behavior in both cases. Looking at the strong lithosphere, now we get a mirror effect of what we saw on the previous slide. So in this case, now that it's harder to bend the plate, for the short plate, we don't see much of a difference. And the reason is that before, in the reference case, we didn't see much of trench retreat anyway. The long plates were more, say, dependent in a way on trench retreat. Since this is now harder to achieve, we see the most reduction in the long plate. So by applying a factor 2, we don't see almost any change. By applying the very extreme factor 10, we see a significant reduction of trench motion to the long plate. This is, if you think about it, a very Earth-like behavior. So for the short plate, making the asthenosphere making the lithosphere 10 times stronger limits the amount of plate moving into the mantle, while it limits the trench motion for the long plate. And we actually get a very similar behavior for both, and you can see that if you look at the bottom right graph, where I show the significance of trench retreat to the overall material converged. So if for the weak asthenosphere and the factor 2 strong lithosphere, we see quite distinct behavior for the short and the long plate, for the factor 10 lithosphere, we see that the behavior of the short and the long plate is quite similar, and it falls into similar values of between 35 and 45%. I should note here that the lithosphere with the factor 10 on it is the most extreme strength that we can think of for plates on the Earth. So even though this is an Earth-like behavior, as we would like to see in our models, we cannot claim that plates on the Earth necessarily behave this way, simply because plates are not that strong, or don't appear to be that strong when we measure them. This is, again, our extreme case that should enlighten the actual measurements. Okay, looking at plate velocities, we get these trends again. We see higher plate velocities with the weak asthenosphere, both for the long and the short plate. But again, the gap between velocities stays about the same as in the reference case. Looking at the strong lithosphere, we see that the velocity of the long plate pretty much stays the same as in the reference case, but the short plate's velocity is being limited and dropped in the extreme case to similar values to those of the long plate. Okay. There are other models that we ran, but I won't show them here. We ran a self-consistent rheology model. So instead of putting factors into different parts of the model, we used a different set of rheological parameters to get the viscosity field that we want, using, of course, the same temperature, strain rate, and pressure fields. We also combined the weak asthenosphere and the strong lithosphere models to get a combined effect, see if that can give us a more Earth-like behavior. And then we ran models with different box parameters to make sure that our results are not biased by our model condition. We want to see that we're actually getting something that is dynamically right. Now, for all of these models, we got similar behavior as in the models that I just showed. So the plate length seems to always affect trench motion, seems to affect plate motion, and of course, plate velocities. Okay, so getting back to the question that I started from. Is basal drag important for subduction dynamics? We think it is, and we base this on the results of our model, and we base this on direct calculations of plates on the Earth. And that's forcing us to look back into the ratio of velocity to the size of plates on the Earth and try to explain what happens there. Why don't we see this trend as we expect to see? In order to do that, we first had to re-examine this plot and to maybe add some more data to it. So this is the present day situation. And like every present day situation, it may be biased to how things are at the moment. What we want to see is how things were, and at least throughout the Cenozoic. We use G plates to extract size and subduction velocity, and trench age for any of these plates. What you see in the graph is the colored reconstruction time of the plate. So how long ago this data exists, with the large points in dark blue representing the present. So by looking just at the subduction velocity to plate size, even throughout the Cenozoic, we don't really get a clear indication of correlation between the two. However, when we plot the size to age ratio, we get a pretty good fit between the two. So that means that at least throughout the Cenozoic, plates that were bigger also had older ages at the trench. Now we use this, the trench age to get a sense of the amount of pull exerted on the plate. The older the trench is, the colder the slab is, therefore it exerts more pull. So now we know that the greater pull is being exerted on bigger plates. Okay, that allows us to explain the ratio of velocity to size. We use the ages to divide this graph into two populations. So the first population is our large plates. These plates have, these plates now we know have higher pull rate, so we expect them to move faster. However, they also have a higher drag rate, so that limits the velocity. And we think that the velocity of these plates is kept at sort of a maximum value by the ratio of possible drag to pull values. The other population, and that's the left side population, is our small plates. Now, we know that the drag for this population is relatively minor. It's not as significant as for the large plates. But now we also know that the pull on these plates is relatively small. So even though there isn't much resistance to motion, there isn't also much velocity developed by the pull of the slab. And of course, as these plates grow bigger, they grow older, they gain more pull, but on the other hand, they gain more drag, eventually moving them into the large plates section where drag is significant, but of course, pull is significant as well. Now, this is based on the main trends of age and size. There are plates that do not follow this ratio. So I marked in several examples here. The Kula and Izanagi at 50 and 60 million years ago, and the Pacific plate throughout its development. And they, because they show a different ratio of size to age, they show different velocity patterns. So for example, the Pacific starts off as a very big plate, but with very young trenches. So it doesn't have much pull, therefore we get a very large plate with very low velocities. The Kula and Izanagi, on the other hand, are not so big plates with relatively older trenches and older slabs mostly, therefore they develop very high velocities. So these populations, they work in a way only for what we observe for most plates throughout the Cenozoic. By examining other plates, we have to make sure at first that the age to size ratio still applies. Okay, so to conclude all of that, in our models, we apply an Earth-like nonlinear rheologies, and we see that subduction velocities are limited by basal drag. That's again in the models. Using these rheologies, the low asthenospheric viscosity leads to subduction with small trench motion that are usually retreating. Now that tells us that lowering the asthenospheric viscosity actually gives us a more Earth-like behavior. On the other hand, an increased lithospheric viscosity requires more energy through bending and is distinct from decreased asthenospheric viscosity. So we see two different mechanisms acting here. It is not the ratio of the two, but each of them affects subduction dynamics and drag in a different way. Now looking at the Earth, the basal drag on the Earth can be equivalent or greater in magnitude to ridge push force for large tectonic plates. And that takes you back to our back of the envelope calculation for the Pacific, where it was significant basal drag. And we suggest that this large significance of basal drag caps the possible velocities of plates on the Earth by negating the increased pull of older plates through their increased size. Thank you all for listening, and please let me have your questions.
Thank you very much, Lior. Please feel free, everyone, to ask questions.
I have one.
Hi.
Okay. Hi. Do you have any estimate how the basal drag and the slab pull increase during the increase of the plate size? I guess it is in a different pace, goes up with the increasing size of the plate.
Yes. Yes. So the way it is increased, let me roll back the presentation. Well, we infer the increase, at least of slab pull, through the increase of trench age. And we know trench age is a factor of the convergence velocity. So that gives you a rate of increase in pull force. That is of course, first order estimate. Pull force can be affected by different things. The amount of flattening of the slab in the upper mantle, in the upper lower mantle boundary, can increase the slab pull. There's actually a work that had been done on very fast plates, where it had been claimed that plates have an increased velocity once the slab pull penetrates the upper lower mantle boundary, and sort of gets this rush of velocity for a very short amount of time until the slab is flattens again. So there are different works about that. You You can infer that from the age of the trench, but actually to get a proper measurement of how much slab pull you have, a tomography of the slab should be done. And it had been done for different plates. There's the slab 2.0 work that tries to reconstruct the global slabs. And you can use that to get a concrete estimate of how things are today. Of course, we don't have that back in time. So we can only estimate through plate velocities how much of this slab was at the surface, how much of it was at the upper mantle. Now, we should say that in most calculations, the pulling part of the slab is only the upper mantle section of it. So it is assumed that the slab at the lower mantle is actually balanced by the higher viscosity of the lower mantle. And most of the pull is being done by the section that is at the upper mantle. I hope that answers your question.
So the slab pull goes up faster than the drag forces with the increase of the plate?
It does for young plates.
Young plates,
For
okay.
The trench is getting older faster than the plate's surface increases.
Yeah, okay.
Increases, we find in measurements for the Cenozoic about 4,000 kilometers long, and this is the square root of the surface size of the plate. So of course, if you have a very elongated plate, things like, say, the Nazca, that has a very long trench, you may get a shift in this ratio. And you actually need to take into account the actual surface area and the trench length and not the square root of them. But it's a good indication, at least first order indication. So yes, young plates become older faster than they become bigger. But then eventually they become big enough, the drag becomes important. So that's, in our calculations, around 4,000 kilometers. Yeah, plates, again, like the Nazca, is a good estimation.
Okay.
Anyone else?
I have a question, if I may.
Yes.
Yes, thank you, Lior, for your interesting talk. Now, I guess your model is 2D model, right?
Yes, yes, as I showed here. Yes.
Yeah, and my question, I have actually two questions. First, how do you think like 3D models will change the result, will influence the result? This is my first question. And the second one is, do you see any correlation between the strength of the asthenosphere to seismic data or very deep earthquakes? I mean, location and rate.
Okay, I'll start with the first one, mostly because it is more of within my field. So actually, apart from these 2D models, and I have to say the fact that they're moving in the side of my eye doesn't help. So these 2D models, they give us some understanding of the system, but of course, Earth is a 3D system, and therefore it should be examined with a 3D model. It's just harder to compute. So we are using now a 3D model. It is a more simplified model. It's not thermomechanical, it's simply a mechanical model, meaning we don't have those thermal effects that allows us for, say, the increase in or decrease in plate thickness. And these are very interesting because if you think about it, trenches don't really end at a vacuum. So at least for the Pacific trenches, one trench, one plate will end at an intersection with another plate. Therefore, we expect that the mantle flow that is created by subduction of one plate should, in a way, affect the neighboring plates. Now, if plates are pretty much similar in size, that shouldn't matter really. But if you have cases like, say, the Pacific plate, and next to it, plate like the Cocos or the Juan de Fuca, or even the Philippine plate, you expect that this plate will be very much affected by the movement of the plates next to them. So this is quite a significant role that bigger plates do. Another part that I've not looked into in these models, and that's the reason why, is the initiation of subduction. So in a 3D model, you can subduct one part of the trench while leaving another part unsubducted. Of course, the unsubducted part will limit velocities because it needs to first break from the original, it needs first to detach from its surface behavior and move into the upper mantle, and then it starts to exert pull forces. So this is something we're not able to model in 2D models. And that's why, for example, when we look at our results, we don't directly compare the absolute value of, say, velocities or basal drag to values on the Earth, because we assume velocities may be higher or lower due to 3D effects. So what we want to see in our models is the same trend as we see on the Earth, but not necessarily exactly the same values. I hope that sums that. Now, your other question was about the seismics and how they correlate with the strength of the asthenosphere. Now, first of all, it's not really my field of expertise. So everything I say can be probably understood better by people who are specifically in the seismic field. But the strength of the asthenosphere is estimated through the movement of seismic rays within this section, mostly through the anisotropy of it. So that's how we get the sense of how much material is flowing there. And I guess that may create higher seismicity, probably around the interchange between the slab and the asthenosphere. But again, I think that's a question that should be asked someone who is actually focused on these fields.
Thank you.
Yeah.
It would be nice to see velocity field in your models to show mantle convection. Does the lithosphere move slower than the asthenosphere, and show the drag force that on the boundary between them? You didn't show them, and I'm sure you have it in your model.
Yes, of course. That is a plot we used in our analysis, but of course hadn't been shown here. What you do get, and I think you can see it here, this is the final stages, is the location of the ridge in those models gives you a sort of an indication of the size of the convection cell. So for example, for the weak asthenosphere model, weak short asthenospheric model, you can see that the convection cell is actually very small in a way.
And is it much slower than the lithosphere?
Then, the asthenosphere and the asthenosphere is, well, not for the weak one, but for the other ones is very well coupled with the upper plate. So there's no weak layer between the two, the same that we apply between the overriding and subducting plate. And yeah, it's about the same velocity. We don't see a driving asthenosphere. So we don't see a case where the asthenosphere is faster than the overriding plate and therefore drives subduction. All of the movement of the asthenosphere is driven by the convection cell, which is driven by the velocity of the slab, which in our case is well attached to the plate. So the velocity of the slab is very much the velocity of the plate itself. We usually get very similar velocities And in the very few cases that we don't, the velocity of the asthenosphere will be lower than the velocity of the plate.
But that's the drag, right?
Yes, that's a drag, of course. Yeah. So we always see a resistive drag, never a driving drag, as some other groups indicated. Actually, we did try to model an active mantle, and we used, yeah, I hope you can see that. Oh, sorry. So what we did is we added another driving force to the system. That will be a plume. So by heating, by adding another source of heating into the model, we're actually able to create a driving asthenosphere, which moves our subducting plate towards the overriding plate and gets us into trench advance region. It may be an explanation in very specific cases on the Earth to why we see this specific trench behavior and why we see such, or we model such high velocities in the asthenosphere. But you have to remember that because it is a 2D model, every plume that we create here is not a rising point, it's not a rising hotspot, but it's a rising wall of hot material, something that is akin to a mid-ocean ridge. So it's not a realistic behavior that we see here. What it is an indication that by adding another driving force, we may be able to move into a driving asthenosphere rather than subducting, rather than resisting asthenosphere.
Well then, there's no question. Lior, thank you very much for a wonderful seminar. We look forward for your visit here.
I hope to visit soon when it is allowed.
Yes. Almost.
Thank you all for participating.